You are the risk manager at a major investment bank. It is 4:55 p.m. The CEO's weekly briefing starts in 30 minutes. On your screen, hundreds of positions, equities, bonds, derivatives, currencies, each one generating its own profit or loss minute by minute, tick by tick. And the CEO will ask you one thing: how dangerous is our portfolio? Not a paragraph, not a chart, one single number. The most popular answer for 3 decades has been value at risk, or VAR. You pick a confidence level, say 95%, and VAR tells you, we will not lose more than this amount on 95 out of 100 days. It is elegant. It is simple. Every bank regulator on earth has demanded it since the mid-1990s. But today, we are going to discover that this number is fundamentally broken. Episode 14, When Risk Satisfies No One. We will build value at risk from scratch, then watch it fail a simple diversification test. We will fix it with expected shortfall, a measure that the Basel Committee now requires every bank on earth to use. And then, we will meet the formula that, in the year 2000, promised to tame default correlations, and 8 years later, helped bring down Wall Street. Let us begin. Before we define anything, we need a convention. In this episode, a positive number means a loss, and a negative number means a profit. With that settled, value at risk at confidence level alpha is defined as the smallest number x, such that the probability of losing x or less is at least alpha. In other words, VAR is the alpha quantile of the loss distribution. In plain English, with probability alpha, our loss stays below this threshold. Now let us see it. Assume our daily loss follows a standard normal distribution, centered at 0 with unit variance. Here is the bell curve, our loss density. At 95% confidence, VAR is 1.645 standard deviations. Everything to the right of this line, the shaded red region, has a 5% probability. That is the tail we are worried about. The parametric formula is beautifully simple. VAR equals mu plus sigma times z alpha. Now watch what happens as we tighten our confidence to 99%. The line marches to the right. The tail shrinks to just 1%. And at 99.9%, we are out at 3.09 standard deviations. The tail is now 1 in 1,000. VAR converts a probability into a distance on the loss axis. There are 3 ways to compute VAR in practice. First, the parametric approach. Assume losses follow a normal distribution, plug in mu, sigma, and the z quantile, and you get a closed-form answer. This is what we just saw. Second, the historical approach. Take the last 500 days of actual returns, sort them, and read off the 95th percentile. No distribution assumption needed. Third, Monte Carlo. Simulate thousands of future scenarios, compute the loss for each, and find the empirical quantile. We built this engine back in episode 4. All 3 approaches give the same answer when the true distribution is known and normal. In practice, they often disagree, especially in the tails. VAR is simple. It is elegant. Every regulator and every bank on earth uses it. But next, we are going to give VAR the simplest possible diversification test and watch it fail spectacularly. Consider the simplest possible diversification scenario: 2 independent bonds. Each bond has a 4% chance of defaulting, which would cost you $100. 96% of the time, you lose nothing. Here is bond A's loss distribution. The tall bar at 0 has probability 96%. The tiny bar at 100 has probability 4%. Since 96% already exceeds our 95% confidence level, VAR at 95% is 0. Bond A looks perfectly safe. Bond B is identical, same distribution, same VAR of 0. Now here's the question that breaks everything. What happens when you hold both bonds together? The combined loss has 3 possible outcomes. 0, if neither defaults. Probability, 0.96 squared, which is 0.9216. 100, if exactly one defaults. Probability, 0.0768. 200, if both default. Probability, 0.0016. Now look carefully at that first cumulative probability. 0.9216 is less than 0.95. That means VAR at 95% is no longer 0. It jumps to 100. VAR of A plus B equals 100, which is greater than VAR of A plus VAR of B, which equals 0. Diversification, the most sacred principle in portfolio theory, just made our risk measure go up. Something is deeply wrong with VAR. In 1999, 4 mathematicians, Artzner, Delbin, Eber, and Heath, asked a simple question: what properties should any reasonable risk measure satisfy? They proposed 4 axioms: monotonicity, bigger losses mean bigger risk, pass; translation invariance, adding a sure loss increases risk by that amount, pass; positive homogeneity, doubling the portfolio doubles the risk, pass; and sub-additivity, combining 2 portfolios should never increase total risk. This is the formalization of diversification. VR fails. We just proved it with 2 bonds. A risk measure that punishes diversification is not just imperfect, it is fundamentally incoherent. But there is a measure that passes all 4 tests. It is called expected shortfall, or CVaR, and it is waiting for us in the next section. VR stares at the boundary and looks away. It tells you where the cliff edge is, but says nothing about how deep the fall might be. Look at this distribution again. At 95% confidence, VR marks the boundary at 1.645. But what about everything to the right, the entire shaded tail? Expected shortfall, also called CVaR, answers the question VR refuses to ask. Given that we fell off the cliff, how far did we fall on average? CVaR is the centroid of the tail. For a standard normal at 95%, it equals 2.063. VAR is the cliff edge. CVaR is the depth of the fall. Formally, CVaR at confidence level alpha is the expected loss, given that the loss exceeds VR. For a normal distribution, this has a beautiful closed form. CVaR equals mu plus sigma times phi of z alpha, divided by 1 minus alpha. The key identity is that the integral of z times the normal density from z alpha to infinity equals phi of z alpha. A one-line proof using the chain rule. Here are the numbers. At 95%, CVaR is about 25% larger than VR. At 99%, the ratio drops to 15%. As alpha approaches 1, VR and CVaR converge because the tail gets so thin that its average equals its boundary. Remember those 2 bonds that broke VR? Let us run CVaR on the same example. CVaR of A plus CVaR of B equals 160. CVaR of A plus B is 103.2. That is less than 160. Sub-additivity holds. Diversification is rewarded as it should be. In fact, CVaR passes all 4 of Artzner's axioms. It is a coherent risk measure. This is why the Basel Committee's fundamental review of the trading book replaced 99% VAR with 97.5% expected shortfall. One important detail: risk measurement always uses the physical probability measure P, not the risk-neutral Q from pricing. We measure real-world losses, not theoretical prices. There is one more gift that CVaR gives us. In 2000, Rockefeller and Yuryasev showed that minimizing CVaR can be written as a convex optimization problem. CVaR equals the minimum over zeta of zeta plus 1 over 1 minus alpha times the expected positive part of L minus zeta. This turns portfolio CVaR minimization into a linear program, fast, scalable, and elegant. We will revisit this formula in the same Math Different World segment, where it connects to adversarial robustness in machine learning. But before that, we need to confront a deeper question. CVaR measures how deep the tail is for a single distribution. But in a portfolio of many assets, how do the tails interact? That is the world of Copulas. Pearson correlation captures linear dependence. It is a single number, and it can be dangerously misleading. Here are 200 points drawn from a bivariate normal distribution with correlation 0.7, a tidy elliptical cloud. Extreme events in one variable rarely coincide with extreme events in the other. Now here is a different data set with the same correlation parameter 0.7, but drawn from a heavy-tailed distribution, a student T with 3 degrees of freedom. Notice the clusters in the corners. When one variable crashes, the other crashes too. When one explodes, so does the other. This is tail dependence, and Pearson correlation is completely blind to it. Same correlation, completely different risk. In 1959, the mathematician Abe Sklar proved a theorem that changed how we think about multivariate probability. Any joint distribution F can be decomposed into 2 ingredients: the marginal distributions, F1 and F2, which describe each variable in isolation, and a copula C, which captures everything about how the variables depend on each other. Joint equals marginals times copula. The marginals tell you the shape of each individual bell curve. The copula tells you how they dance together. When the marginals are continuous, the copula is unique. This is not an approximation. It is an exact decomposition. The copula captures only the dependent structure, completely freed from the marginal distributions. You can swap in any marginals you like, and the copula stays the same. Here is the trick that makes copulas work. Take any continuous random variable x and pass it through its own cumulative distribution function, u equals f of x. The result is always uniformly distributed between 0 and 1, regardless of the original distribution. This is the probability integral transform. Now apply this to both variables simultaneously. x1 becomes u1, x2 becomes u2. The copula is the joint distribution of these transformed variables, living on the unit square. Both marginals are uniform by construction. Everything that remains is pure dependent structure. This is why the copula is such a powerful abstraction. It strips away the individual shapes and isolates the relationship. This is the central insight. Two portfolios can have identical individual risk profiles, identical correlations, and yet completely different joint risk, depending on the copula. So what happens when you choose the wrong one? In the year 2000, a financial engineer named David X. Lee published a paper that used the Gaussian copula to model default correlations. 8 years later, Wall Street burned. In the year 2000, David X. Lee published a paper in the Journal of Fixed Income. He proposed using the Gaussian copula to model default correlations among mortgages. The formula is deceptively simple. Transform each default probability through the inverse normal CDF, assume a bivariate normal joint, and a single correlation parameter RO captures everything. The CDO market loved it. Issuance exploded from $69 billion in 2000 to $500 billion by 2006. One correlation parameter to price billions in structured credit. It seemed too good to be true. It was. Let me show you what the Gaussian copula density looks like in 3 dimensions. Each axis represents a uniform probability. The height is the copula density. Notice the center peak. In the middle of the distribution, the Gaussian copula works fine. But look at the corners. The lower left corner where both variables crash simultaneously. The upper right corner where both explode. The Gaussian copula density is almost flat there. Mathematically, the upper tail dependence coefficient lambda u equals exactly 0. The Gaussian copula assumes that simultaneous extreme events are asymptotically impossible. Now replace the Gaussian copula with a t-copula, same correlation, but with 3 degrees of freedom. Look at the corners now. They spike upward. The t-copula assigns real probability to simultaneous extremes. When one variable crashes, the other is likely to crash too. The tail dependence coefficient lambda u is 0.312, not 0, significantly positive. This is the mathematical fingerprint of tail dependence. The Gaussian copula is structurally incapable of seeing it. In 2008, subprime mortgage defaults became massively correlated. Entire neighborhoods defaulted together. The Gaussian copula assigned this event a probability of effectively 0. ADA-rated super senior CDO tranches, supposedly the safest paper on Wall Street, absorbed catastrophic losses that the model said could not happen. Felix Salmon wrote in Wired magazine, "The formula that killed Wall Street." But Lee himself had warned, very few people understand the essence of the model. VR and CVaR are powerful, but they share a limitation. They rely on historical data or assumed distributions. The real world delivers shocks that no model predicted. Black Monday in 1987, a 22.6% drop in a single day. The 2008 crisis, a 56% drawdown. The COVID crash of 2020, 33% in 5 weeks. Stress testing fills the gap with imagination. You ask, what if interest rates spike 500 basis points? What if oil hits $200? And there is an even more powerful variant, reverse stress testing. Instead of asking what could go wrong, you start from the worst possible outcome, your portfolio is destroyed, and work backwards to find which scenario would cause it. This flips the question. Not what is the probability of disaster, but what does disaster look like? And now, the connection that makes this episode a bridge between 2 worlds. Same math, different world. On the left, CVaR minimization. The Rockefeller-Uriasev formula from section 4. Minimize zeta plus 1 over 1 minus alpha times the expected positive part of loss minus zeta. On the right, distributionally robust optimization. In machine learning, you want your model to perform well not just on the training distribution, but on the worst-case distribution in a neighborhood. These two formulations are mathematically equivalent. The CVaR objective in finance and the DRO objective in machine learning are the same optimization problem, viewed from different angles. The neighborhood is a phi divergence ball, where the likelihood ratio is bounded by 1 over 1 minus alpha. Tail risk management in finance and adversarial robustness in AI. Same math, different world. Same math, different world. Let us take a step back and see what we built in this episode. We started with value at risk, the industry standard for 30 years, and discovered it punishes diversification. We learned the 4 axioms that define a coherent risk measure. We met CVaR, the measure that passes all 4 tests and looks not just at the cliff edge, but at the average depth of the fall. And we saw how the Gaussian Copula's structural blindness to tail dependence helped trigger the worst financial crisis in 80 years. But this episode is more than a standalone lesson. It is the final chapter of Phase 2. Over 9 episodes, we built the complete mathematical engine of modern finance. Probability foundations, Brownian motion, stochastic calculus, the Black-Scholes equation, the Greeks, risk-neutral pricing, portfolio optimization, and now, risk measurement. 9 episodes. One coherent mathematical structure from the axioms of probability all the way to the formulas that every bank on Earth uses today. And now the question that Phase 3 will answer. We measured fat tails. We saw that the Gaussian copula misses them, the t-copula captures them. But where do fat tails come from? Phase 3 introduces the generators, the Heston model, where volatility itself is random, and Merton jump diffusion, where prices can leap without warning. The t-copula showed us the result. Phase 3 reveals the cause. The math behind finance, Phase 2 complete.